All right, welcome back to Fundamental Theorem of Calculus Antiderivative part. And what I want to do now is I want to look at what happens if we have a variable lower limit. Whoops, that was weird. Variable lower limit. All of our examples so far have had a constant value for the lower limit. So let's look at y equals the integral from x to 5 of 3t sine of t dt. And notice that all we've done is switch the limits. Instead of being from 5 to x, now we're saying, well, let's go from x to 5. Well, this is a fairly straightforward one because, as we have discussed before, we can put a negative sign in front of it and just go in the opposite direction. So the derivative of y with respect to x in this case would just be the negative of what it would have been anyway. So a slightly more complicated situation. What if we have two variable limits? Let's say we start at 2x and we go to x squared. And we'll do 1 over 2 plus e to the t dt. So what we've got here now is we've got something where what do I do with this? That's not a constant. I can't just say doesn't matter, because when I take the derivative, it certainly will matter. So what I'm going to do instead is I'm going to split this up into two derivatives. I'm going to say, well, let's go from 2x to 0, 1 over 2 plus e to the t dt. And then let's go from 0 to x squared, 1 over 2 plus e to the t dt. And if you think about this in terms of area, if I've got some function and I want to know the area from 2x to x squared, there's absolutely no reason that I can't just split it up and say, well, let's find this one, and then let's find this one, and then let's add them together. So now I'm going to do with the first part what I did with the previous example, which is make that a negative. Things are popping up all over the stop, go away. There we go. The negative from 0 to 2x of 1 over 2 plus e to the t dt plus 0 to x squared of 1 over 2 plus e to the t dt. And now we've got to do a little bit of chain rule substitution. We know that without going through all the steps that the first half will be equal to the derivative of 2x times, almost forgot to put that negative in there, the derivative of 2x times this right here, remembering that we need to put in the 2x right here. So there's the derivative of u, and there's 2 plus e to the power of u. And then on this one, we've got the derivative of x squared, and then u again becomes our input. And so my derivative, just remembering that this is u, there's the du dx. In this case, this was u, and so this is du dx. And then this is dy du, and this is dy du. All right, so there's our final answer. Let me go ahead and write it out. Dy dx equals negative 2 over 2 plus e to the 2x plus 2x over 2 plus e to the x squared. There's my derivative of that initial function. So my students, why don't you go ahead and do exercise 19. I'll ask you to do a chain rule problem. And what I want to do here is squeeze in one more example. So we'll call this example 4. What if I am given a derivative? So what we've got here is that the derivative of y with respect to x is equal to tan x, and we're given a value of the function, f of 3 equals 5. So there's a point on this graph where x is 3, y is 5. So let's start by just saying y is equal to the integral from 3, our x value, to the x of tan of t dt. And hopefully we're comfortable with the idea that if I take the derivative of y, that's just the derivative of a to the integral from a to x of the function with respect to t. But here's the problem. According to this, if I find y of 3, that would be the integral from 3 to 3 of tan of t dt, but that's equal to 0. And I'm already told that y of 3 is not, in fact, equal to 0. It's equal to 5. Well, how do I make this function equal to 5? I just add 5. Y is equal to the integral from 3 to x of tan of t dt plus 5. Now, think about putting in a 3 for the x. The integral from a to a is 0 because you have a rectangle of width 0, plus 5. That gives me my initial value. There is my function. So notice nothing changed when we went from here to here, because if the derivative is the function, then we just can shove it into the integral. And the reason we chose to put a 3 here was because we knew the value of the function when x was equal to 3. And everything else is just standard. It's always dt. It's always to x for a situation like this. And then it was just a matter of how do we get from 0 to 5? Well, we just added 5 to get there. All right. My students, go ahead and do exercise 25. And we will be back with another exploration in the next video. Thanks for watching.